Hi everyone, I'm Cheryl. In this problem, we're going to be finding upper and lower sums to help us get an approximation of the area under the curve y equals 5x squared, bounded by 0 and 1, and the x-axis. So the first thing I want to notice is that my function is an increasing function. So if I'm going to use rectangles to approximate this area, an upper sum would be used by using the right endpoint, because notice if I use a right endpoint, my rectangles will have a larger area than the area under my curve. So I need to find widths and heights of these rectangles. So first of all, let's talk about the width. Now, in this problem, I didn't tell you how many rectangles to use, so we're just going to have to leave it as n. So the width of any of those rectangles is going to be b minus a divided by n. In this case, 1 minus 0 over n, or 1 over n for my width. Now for my height, I need to use the right endpoint. So the x sub I, which will be the endpoints of my interval, is going to be the first point, or the leftmost endpoint. I'm going to call that a for now, plus a width times I, b minus a all over n times I. So think about what happens in this particular case. In this case, the leftmost endpoint is 0. I've already calculated b minus a over n to be 1 over n. I'll multiply that by I, and I get I divided by n. So think about what happens. If I make that first rectangle, and I make my first subinterval point here, what's the right endpoint? Well, it's going to be 0 plus 1 width. And 1 width is 1 over I. So I is 1, and I've moved 1 width. If I want to move to my second rectangle, I have to move 2 widths from that initial starting point. So I will be 2, and I will be at 2 over n. So you can see this will give me the right endpoint at any subinterval along the way. Okay. So what is the formula for finding the upper sum? Well, it's the summation from I equal 1 to n of f of x sub I times delta x. And again, think about what this is. The f of x sub I is going to give me the height of a rectangle. The delta x is going to give me the width. The product will be the area of the rectangle. The summation tells me I need to take the sum of all of the rectangles as I go across. Okay, so let's fill in the details for this problem. I have the sum from I equal 1 to n of f of x sub I. I've calculated that x sub I will be I over n for this problem. So f of I divided by n times delta x, which I've calculated for this problem to be 1 over n. Okay, the next step is going to be to do some function evaluation. I want to calculate what f of I over n is. So I'm going to leave the summation alone. I'll worry about that later. F of I over n is going to be 5 times I over n squared. And then I'm still multiplying by 1 over n. Okay, the next step is to do some algebra to simplify this expression. So I have the sum from I equals 1 to n of 5 times I squared divided by n squared times 1 over n, which further simplifies to 5i squared all over n cubed. Now, in this particular problem, I'm ready to deal with my summation, and I is what is moving from 1 to n. As far as I is concerned, the 5 over n cubed is a constant. So that can be pulled out, 5 over n cubed, and then I'll be summing I equals 1 to n of I squared. Now we have a formula for this. I'm going to move this up over here, and I'm going to say that I have 5 over n cubed times. This is really, if you think about it, 1 plus 2 plus 9 plus 16. And the formula for that is you can take n times n plus 1 times 2n plus 1 and divide it by 6. And it's exactly the same thing as summing up all of those squares. So once I notice that, I'm back to some algebra. So let's see. I notice that this n will cancel with one of those, and I have 5 times the quantity n plus 1 times the quantity 2n plus 1 all over 6n squared. Some more algebra. I'm going to go ahead and use FOIL on those two binomials, and I'm going to end up with 2n squared plus 3n plus 1, and again it's all over 6n squared. I'll go ahead and distribute the 5. I've got 10n squared plus 15n plus 5 all over 6n squared. Okay, one more thing. I'm going to take this fraction and I'm going to split it. I'm going to split it as 10n squared all over 6n squared plus 15n all over 6n squared plus 5 all over 6n squared. And then I can reduce each of those individual fractions. Okay? The n squareds here completely cancel, and 2 divides evenly into both 10 and 6. I end up with just 5/3. In the second fraction, this n cancels with one of those, and I can divide 3 evenly into both pieces, and so I end up with a 5 all over 2n. And in the last part, nothing cancels, so I'm just left with 5 over 6n squared. All right, because I was not told how many subintervals to use or what the value n is, that's as far as I can go. And that's my upper sum for this problem. Now we'll go ahead and look at the lower sum. Now we're ready to find the lower sum. Well, like before, we're going to come over to our graph and we're going to look at subintervals. So if I just mark a couple of those off to get an idea of what's happening, I notice that if I'm looking at rectangles using a subinterval, because my function is increasing, I'm going to get the lower sum, or the smaller value, by using the left endpoint. So I'm going to need to find a left endpoint so that I can calculate the height, but I also need the width of one of those rectangles. Well, the width is just like what happened with my upper sums, because the width is going to be b minus a divided by n. And I wasn't told what the value n is this time, so all I can do is say it's 1 minus 0 divided by n, or 1 over n. Now the part that's different is this time my x sub I, which is going to indicate the x-coordinate of my subinterval, I want it to be the left endpoint. So I'm going to start with it being equal to the initial left-hand point plus my width, b minus a over n, times the quantity I minus 1. So what does that do? Well, it starts me out at the initial spot and tells me to move a width, but I have to back off 1. So if I'm on my first rectangle, notice 1 minus 1 is 0. I'm not moving any widths at all. That puts me my left endpoint right at the initial starting position. If I'm going to move 2 rectangles into it, here's 1, 2, so I is going to equal 2. I'll start at my initial point, but I'm only going to move 1 width. That's going to put me at the left endpoint of that second subinterval. Okay, so for this particular problem, a was 0. We already calculated b minus a over n to be 1 over n, and I'll have that times the quantity I minus 1. So I have I minus 1 all over n. Okay, so now I'm ready to plug it into my formula. My formula looks just like the upper sum formula because this first piece is the height of my rectangle, the second piece the width. So that will give me the area of a representative rectangle. But then I'm going to sum up all the areas of my rectangles. The thing that's going to make it different, though, is the value that I'm plugging in to the x sub I, because I'm going to use the left endpoint this time. So this will be f of I minus 1 divided by n. And then I'll multiply by my width, which was still 1 over n. Okay, next is some function evaluation. I need to evaluate the function when the input is I minus 1 over n. So I have 5 times the quantity I minus 1 all over n squared. And then I'll multiply by 1 over n. Okay, now it's time to do some algebra. I'm going to go ahead and square I minus 1 over n. So I've got 5 times the quantity I squared minus 2i plus 1 all over n squared. And then we're multiplying by 1 over n. So I got that numerator by performing FOIL on the quantity I minus 1 squared. Okay, so now a little more algebra. I equals 1 to n. I'm going to have 5 times the quantity I squared minus 2i plus 1 all over n cubed, multiplying those two fractions together. And now I notice that 5 over n cubed is really constant when you're looking at the sum from I equal 1 to n. I is the thing that's changing. So that 5 over n cubed I can pull outside of my summation. And so I have 5 over n cubed times the sum I equal 1 to n of I squared minus 2i plus 1. All right, I'm ready to do my summation. I also notice that when I'm doing a summation of 3 pieces that are either added or subtracted, I can do the summation of each piece individually. And I have some formulas for that. So let's move up here. And I'm going to have my lower sum being equal to 5 all over n cubed times. The first part of my formula is the sum from I equal 1 to n of I squared. That formula is n times n plus 1 times 2n plus 1 all over 6. The second piece, I'm going to be subtracting the sum I equal 1 to n of 2i. 2 is a constant that can be pulled out, and the formula for summing I from 1 to n is going to be n times n plus 1 all over 2. And then the last piece is just summing 1. Now this is 1 plus 1 plus 1 plus 1, n times. And so that's the same thing as n. All right, so I have all my formulas for the summation taken care of. Now I have a lot of messy algebra to go through to simplify this. So I've got 5 over n cubed. And let's get a common denominator of 6. And in this first fraction, it's already over a denominator of 6, so I don't need to do anything else, but I think I'll go ahead and multiply out that numerator. So first I'll do FOIL with the quantity n plus 1 and 2n plus 1. So I have n times the quantity 2n squared plus 3n plus 1. Okay. Now, for the second fraction, I want to write that as the denominator of 6, so I'm going to have to multiply the numerator by 3 as well. So if I multiply top and bottom by 3, I'm going to end up with 6n times n plus 1 all over 6. And then on the last piece, to get a denominator of 6, I'll have to multiply the numerator by 6 as well. So I have 6n. Okay, I'm not done with the algebra yet. So I've got 5 over n cubed. I'm going to go ahead and distribute the n across. So I have a 2n cubed plus 3n squared plus n minus, distributing the 6n, a 6n squared minus 6n, and then I still have my plus 6n. It's all divided by 6. Now in the numerator, I notice I can combine some terms. So I've got 5 over n cubed times 2n cubed, and I have a 3n squared and a minus 6n squared, which will give me a minus 3n squared. And I have a plus n, a minus 6n, and a plus 6n, so that'll just give me plus n. And all of that is over 6. Okay. Now that I have two simplified fractions, I'll go ahead and multiply them together. So that gives me a 10n cubed minus 15n squared plus 5n. And that's all divided by 6n cubed. Okay, some more simplification. I'm going to take this fraction and split it into pieces. So I have 10n cubed divided by 6n cubed. And minus 15n squared divided by 6n cubed. And finally, 5n divided by 6n cubed. Each of these fractions can be simplified. I noticed that the n cubes cancel in that first fraction, and I have 10 over 6. And 2 divides evenly into both of those pieces, so I can simplify it to 5/3. In my second fraction, the n squared cancels, and I'm left with one n in the denominator. And I also noticed that 3 will divide evenly into both of those numbers, so I end up with minus 5 all over 2n. And in the last piece, the only thing that cancels is one of the n's. So I'm left with 5 all over 6n squared. And now it's simplified, and that will give me my lower sum. I hope that was helpful. Thanks.